Alright, so this is a screencast on uncertainty and graphical analysis. So if we have an example with a roller coaster rolling down its first descent, the total energy of the roller coaster is equal to its kinetic energy plus its gravitational potential energy. So I'm going to give you some parameters here. The mass of the roller coaster is 1500 plus or minus 10 kg, velocity is 30 plus or minus 5 meters per second, and the height that the roller coaster is currently at 75 plus or minus 2 meters. So what if I asked you to calculate the absolute and percentage uncertainty in U, the total energy? Well, first of all, the kinetic energy is just equal to a half mv squared. So if I fill in all my values for that, I get that the kinetic energy is 675,000 joules. The gravitational potential energy is calculated as mgh. So if I fill in all my values for that, I get 1,103,625 joules. So my formula for calculating the total energy was the kinetic energy plus the gravitational potential energy. And if I add those two together, then I get a total of 1,778,625 joules. So that's my value for U. And that's a function involving addition. So I'm going to use Rule 1 for uncertainties. Rule 1 is to do with functions using addition or subtraction. And it says that to find the absolute uncertainty in U, I have to add the absolute uncertainty in the kinetic energy and the absolute uncertainty in the gravitational potential energy. But kinetic energy is equal to a half mv squared. So I want to calculate the absolute uncertainty in the kinetic energy or in the gravitational potential energy. I'm going to have to use my other rules. So for example, with my formula for kinetic energy, I have a half times m times v squared. So first of all, this is a function involving multiplication. It's m times v squared. So I have to use my second rule. Rule 2 is to do with functions involving multiplication or division, and the rule is add the fractional uncertainties. So the fractional uncertainty in the kinetic energy will equal to the fractional uncertainty in the mass plus the fractional uncertainty in the velocity. But if I start to fill out my values there, I have to stop here. A fractional uncertainty in v squared. This is a function involving powers. Therefore, I use Rule 3. So for functions involving powers, I multiply the fractional uncertainty by the power. So in other words, if I'm looking for delta v squared over v squared, I find that by multiplying delta v over v, the fractional uncertainty in v, by the power. In other words, the fractional uncertainty in v squared is equal to 2 times the fractional uncertainty in v. Okay, so I've used all three rules here for uncertainties. So I just fill in my values. 2 times delta v is 5 over v is 30. And I calculate that the fractional uncertainty in the kinetic energy is 0.34. But from my rule up here, I know that to calculate the absolute uncertainty in U, I need to add the absolute uncertainty in the kinetic energy plus the absolute uncertainty in the gravitational potential energy. So here I have a fractional uncertainty, so I need to get this back to absolute uncertainty. And I get that just by multiplying the fractional by the actual value. All I'm doing really here is cross-multiplying. So therefore the absolute uncertainty in the kinetic energy is equal to 0.34 times the kinetic energy itself. And so my absolute uncertainty in the kinetic energy is 229,500 joules. So I'm halfway there. Now I calculate GPE, gravitational potential energy, using a function mgh, which involves multiplication. So I'm going to use Rule 2 for that, add the fractional uncertainty. So the fractional uncertainty in the gravitational potential energy will equal to the fractional uncertainty in the mass plus the fractional uncertainty in the h. Now if you look at this and you say, well, what about g? What about gravity? Well, I didn't define any uncertainty in my g value over here. So generally we take g as 9.81. Obviously, depending on how you measure that experimentally, if you did measure it experimentally, you'd have some error in it. But in this case, we're not measuring it, we're just using a value for gravity. So there's no uncertainty in the gravity value in this case. Just like up here when we calculated the uncertainty in the kinetic energy, there was no uncertainty in the half. That's just a number, right? So, again, to find the fractional uncertainty in the gravitational potential energy, I add together the fractional uncertainty of the mass plus the fractional uncertainty of the height. It's nice and easy. I just fill in my values, and I get that the fractional uncertainty in the gravitational potential energy is 0.03. So again, to get back to absolute, all I have to do is multiply the fractional by the actual amount. So in other words, multiply 0.03 by whatever my value was for GPE. And I get the absolute uncertainty in the gravitational potential energy as 33,109 joules. So we're almost there. All I have to do to calculate the absolute uncertainty in U is add together the absolute uncertainty in the kinetic energy plus the absolute uncertainty in the gravitational potential energy, and I get 262,209 joules. So to find the percentage uncertainty in U, then all I do is I get the fractional uncertainty, delta U over U, and multiply it by 100. I'm calling this the percentage uncertainty here, percentage delta U. Really, I should probably express it like this, but you get what I mean by this anyway. So the percentage uncertainty in U is the fractional uncertainty in U multiplied by 100, which gives me 14.74%. Okay. Now, let's look at some graphical analysis here. So let me actually go back there for a second, and I'll explain first of all that this is just an equation that relates the stopping distance d with the velocity of a moving car. So if a person was told to apply the brakes at a particular velocity, and then they measured the stopping distance, and they repeated this experiment for a set of different velocities, then we can define the stopping distance d as equaling v squared over 2a plus v times t, where v is the velocity, a is obviously the acceleration, and t is the thinking time. So the thinking time is just the time that it takes from when the person is told to put their foot on the brakes to the time that the car actually starts braking. So there'll be a little bit of a difference there because of reaction time. So if I plot a graph of d against v, I won't get any type of linear relationship that will actually help to prove this, this equation or this relationship. But if, on the other hand, I plot a graph of d over v against v, then I do get a straight line. Okay? So the equation of any straight line is equal to y is equal to mx plus c. Yeah? So my job is to equate this with this formula here. So it's almost in the form y is equal to mx plus c, but you can see here that if this line is y is equal to mx plus c, then first of all my y value has to equal whatever's on the y-axis, and my x value has to equal whatever's on the x-axis. So in other words, y in this equation has to equal d over v, but up here it doesn't equal to d over v. So for now, I'm just going to say that d over v is equal to k, some constant, times v plus c. So again, this is in the form y is equal to mx plus c. So y, or y is d over v, that's on the y-axis, is equal to some constant times v plus c. So it's my job to try and figure out what that constant is, or what that something is. So the constant will equal to m, the gradient, and c here will obviously equal to c in my first equation, which will just be the intersect down here. So if I want to equate this equation with this, I have to rearrange this equation a little bit. So if I know that my y value has to equal to d over v, then I'm just going to divide this side of the equation by v. So then I'll have it in the form where at least my y value matches what's on the y-axis. So if I divide d by v, I also have to divide this entire side by v. So what do I get? Well, if I divide v squared over 2a by v, then I just get v over 2a. And if I divide Vt by V, then I just get T. So now I've rearranged this formula into a form where it matches the equation of my line. It's in the form y is equal to something times V plus some constant C. In this case, it's the thinking time T. So it's in the form y is equal to mx plus c. So in other words, it's in the form y, where y equals d over v is equal to something, and I need to isolate that something. That something is 1 over 2a in this case, times v, because 1 over 2a times v is the same as saying v over 2a, plus the thinking time t. So now I can identify what the gradient of the line will give me. It'll give me 1 over 2a, and the intersect c will give me thinking time. Okay? So the trick is to try and find as many of these experiments as you can where the directly proportional graph is equated to some formula, and see if you can rearrange that formula in order to get it into the form y is equal to mx plus c.